particular day that we would like to visit. For this reason, they have shifted us to another treatment plant which is located in Anstec, in Bandar Anstec, which is about 40 minutes from UPM. I'm currently waiting for the official letter from IS Selangor. Once I've received the official letter, I will need one of you to arrange for the bus to go for the formalities for us to get the bus. So for now, can I get someone to volunteer for the bus arrangement? Anyone can help me to arrange for the bus?
I think I can. What?
Who can?
Nurin.
Oh, Nurin. Okay, great. Nurin. Boleh ke Nurin? Nurin?
Boleh ke sebab ada group lain yang dah pernah buat tempah bas.
I
Nanti saya
see.
tanya dia.
Okay, alright. Okay, thank you very much, Nurin, for your willingness to help me arranging for the bus. So I will get in touch with you once I receive the official letter. They rang me yesterday and they asked permission to change from Semenyih water treatment plant to that one is Sungai Labu water treatment plant. The one that we are going to visit is um, uh, the one that we are going to visit is going to be the Sungai Labu water treatment plant. This is 40 minutes from UPM. Yeah, so there are going to be 32 participants, 32 students who are going to join us. 24 from this course is compulsory for all of you to join the visit. Yeah, it's a part of the lecture where the visit will be held on the 14th of June, which is on Tuesday. Yeah, 14th of June on Tuesday. Uh, Hope that we can depart from UPM at 1:45 p.m. Yeah, after solat tu. We can depart from UPM at 1:45, so we shall arrive at Sungai Labu Water Treatment Plant around 2:30, so we can spend about 1 hour and 30 minutes over there. Before 4:30, I hope that we can depart to UPM because there will be 8 students, which is a master student, who will also joining us for this visit. They will need to come back to UPM before 6 p.m. because they will have another lecture, not with me, with other lecturer. For this reason, we have to depart earlier from water treatment plant so that they can get ready for the lecture at 6 p.m. Yeah, I will detail once we have confirmed about the bus. I will let Nurin know. I will keep you posted regarding on this visit. All right. Thank you very much. Thank you again, everyone. I have checked your tests. Yeah. Most of you can answer the question. There are few more. I need some time. Yeah, I need more time to check. So next week, we shall spend about 30 minutes to discuss about your test, where I will return to each of you, yeah, the answer script. Maybe only one, two of you for now. For the time being, only one or two of you require special attention. The rest, I think you are doing fine. But let me finish the marking the answer script, and we shall conclude the performance up to week 7. Okay, now let me share my slide. We have completed our for information, we have completed our lecture on biological treatment. Yeah. So today we are going to explore the new subtopic for the water and wastewater treatment. The subtopic that we are going to explore today is normally used for both water and wastewater treatment, which is known as adsorption technology. Yeah, adsorption technology. Yeah. So this is one of the physical chemical treatment system. Yeah, it is involved physical as well as a chemical treatment. Yeah, that's why adsorption is known as physical physical treatment, yeah, physical chemical treatment, because it's involved both physical as well as a chemical process during the treatment of water or wastewater. In water application, in water treatment application, adsorption system, yeah, where they use activated carbon, yeah, is one of the adsorption technology. It is now a compulsory, yeah, for each of the water treatment plant to employ adsorption technology, which is the activated carbon, yeah, so that it can further remove the dissolved material. Yeah, that's why adsorption is not something very new in water treatment system. In fact, we have employed the activated carbon, yeah, which is, if you can see in my slide here, the one in black here, yeah, this is the activated carbon. The activated carbon which is in black in color here are derived from the charcoal, while the one that on my left side, which is orange in colors, are derived from fruit peel. If I'm not mistaken, this one is from this one derived from orange peel, yeah, so the activated carbon. So in water treatment plant, normally the activated carbon are being incorporated during a filtration process. Yeah, so we have explored about the filtration system, the needs for the backwashing, and we know that the bottom part of the filtration system will be the gravel, yeah, followed by the sand layer, and after the sand layer will be the activated carbon. So the role of the activated carbon, yeah, is to remove the dissolved minerals, because most of the dissolved minerals cannot be removed during coagulation, cannot be removed during flocculation, cannot be removed using gravel or sand. They can only be removed using the adsorption technology, which is the activated carbon. Okay, that one is water treatment. In wastewater treatment, normally adsorption technology are being employed as a post-treatment, as a polishing techniques. For example, if there are substances left in treated wastewater, for that reason, adsorption technology can be used, can be employed as one of the option for further removal of the left substances. All right. So lecture 9, we are now in lecture 9, the adsorption. So you can see in this figure, so from oil palm tree, 10% it will produce oil and 90% will be the biomass. So part of the biomass, which is the oil palm fronds, the fresh fruits bunch, as well as oil palm trunk. These are considered as the residual. Residual. So this residual which is known as biomass are to be employed for the development of the adsorbent. They can be, you can see here, some of them are being developed as the cake, as the shell, as the branch, as well as the fiber. So these four options, these four types of residual, all these residual can be used to develop the adsorbent. Okay. Okay. The one that I have been talking today is about the adsorbent. There are a few terms that you have to familiarize. The first one is the terms of slightly out. The term known as adsorbent. So what is adsorbent? Adsorbent is the material that can be used to remove pollutant. Material that can be used to remove pollutant. So so the role of the adsorbent is to is to adsorb the pollutant onto. Now you have to be careful with the sentence. Onto the surface of adsorbent. Okay, you will find another term which is known as adsorbate. And what is adsorbate? Adsorbate is the pollutant to be removed. Okay, let me adjust the font. Control E. Okay, so adsorbent is the material, yeah, that can be used, yeah, to remove the pollutant. Yeah, that's why it can be derived from charcoal, it can be derived from biomass, it can be derived from agro waste. Yeah, so and the role of the adsorbent is to absorb, yeah, absorb the pollutant onto the surface of the adsorbent. That's why I said just now, when we employ the adsorbent, yeah, in the water or wastewater treatment system, they actually absorb the pollutant onto the surface only. Okay, while you will see another term which is known as adsorbate. Yeah? Adsorbate is the pollutant to be removed. Let's say you would like to remove the dissolved mineral. So in this case, the dissolved minerals is the adsorbate. Yeah. So sometimes we need to remove the inorganic material. Inorganic material like methylene blue. Methylene blue. So methylene blue is very common in textile wastewater. So because they are used as a part of the color, textile wastewater, textile industry. Not only that, from the in any of the industrial wastewater, they do produce the methylene blue. So that normally methylene blue can be effectively removed using the adsorbent. So in this case, the methylene blue is the adsorbate. Another term, which is very common too, which is known as adsorption. Yeah. Okay, now adsorption. Okay, what is the difference between the one with the B as well as the one with the P? Yeah, this one with the P. Okay, the difference is absorption is a system, is a system also kind of pollutant removal, but the mechanism is different. When we employ the absorption, for example, you use a tissue paper to clean up the spilled water, so it will absorb. So it will absorb into the cell of the material. So the difference is when we use absorb. Sorry. Absorb. This is what I want to tell you. Absorption. Okay. The first one is the D, adsorb. The one that we would like to study today is adsorb. Okay, and you will see another term which is absorb. So in my following video, in the following video, I will share with you to how to differentiate between adsorption as well as absorption. But in layman definition, how do we differentiate between these two mechanisms is when we employ adsorption technique, it will only absorb onto the surface of the material. So but if you employ absorbent, meaning to say that it will absorb the pollutant, onto this into the single cell, into the cell of the material. So for this reason, normally adsorbent, it can be dissolved, it can be recycled, it can be reused. While the absorb, for example, like tissue paper, it cannot be reused. It cannot be reused because we cannot dissolve the we cannot remove the pollutant. Okay, I will explain more later regarding on the difference between these two, but in the following video I believe that you will understand better. But just to get you familiar, the difference between what is the difference between AD and AB process. Yeah, AB process, for example, like when you use a tissue paper to clean up the spill water, it will absorb the liquid, yeah, into the cell of the material. But for adsorbent, it only absorb the pollutant onto the surface of the adsorbent. For this reason, whenever we employ the adsorbent, for example, the activated carbon in water treatment plant, we can dissolve. Yeah, we can dissolve. So this is why we have to conduct the backwashing process. Yeah, because the pollutant only stick on the surface of the adsorbent. That's why we can dissolve. We can remove the pollutant. Okay, so these are the advantages of using the adsorption technology. Okay, so these are the summary, yeah, the summary of the technology that can be used for the removal, yeah, of methylene blue. MB is the methylene blue. So overall, yeah, we have adsorption technology. Yeah, we have adsorption technology. If I can, adsorption, the one that we would like to study today. Yeah, we also have electrochemical treatment, chemical precipitation, coagulation and flocculation, ion exchange technique, membrane filtration, as well as the aeration system flotation. But the one that we are going to focus in detail today, yeah, is about the adsorption technology. Yeah. So adsorption technology, yeah, is a system, yeah, where is involved is comprised of activated carbon, nanoparticles, carbon nanotube, yeah, and natural material, bioadsorbent, and a low-cost adsorbent. So these are the technology that we are going to explore, yeah, in these topics. Yeah. Okay. So let's go one by one. This is actually from a journal published by my recently by my PhD student, was published in February 2022, 3 months ago. So all of these figures are copied from the journals. I've put the citation here, Hamad and Idrus. So, and this is also from the journals. Okay, research on carbon-based adsorbent and sources of activated carbon. Okay, we have carbon-based adsorbent. Yeah, these are the adsorbent that can be used to remove the pollutant. Yeah. First, we have the activated carbon as well as modified activated carbon. Yeah. On top of activated carbon are the most popular adsorbent. The most popular adsorbent, because you can see here, yeah, 58% of the carbon-based adsorbent are derived from activated carbon, whether it's a modified activated carbon or non-modified activated carbon. And the rest, it can be biochar, graphitic carbon, porous carbon, as well as carbon nanotube. Yeah. So the one that we are going to discuss in our syllabus is on activated carbon. Yeah, because they are very common. Yeah, they are very common, used in water or water treatment. Okay, if you would like to look in detail, yeah, activated carbon, you see, yeah, for 58% activated carbon, then can we, so let's look in detail. What does it comprise? Yeah, so 83%, yeah, of the activated carbon are derived from agro waste. Yeah, 83%. They are derived from agro waste. Okay, they are derived from agro waste. While 9% are the coal, right? 3% are the animal waste, 2% are derived from the wood, yeah, and the rest they are derived from the sewage sludge. Yeah? So don't forget, yeah, the sludge, yeah, whether sludge from water treatment plant or wastewater treatment plant can be used to develop the activated carbon, not only agro waste beds. Yeah? So, but agro waste beds are the most popular sources to develop the activated carbon. Okay, next slide. This is also from the journals. Yeah, so numerous inexpensive adsorbent. So the advantages of employing the adsorbent is they are very low in terms of cost. Yeah, but sometimes it can be low in terms of cost, in terms of the capital cost, but not exactly in terms of operational cost. Yeah, because we have to promote the regeneration, we have to promote the desorption to clean up the to remove the pollutant. Yeah, so we have to. It can be further investigated in terms of the total cost required. Yeah? So let's look at the capacity, absorbent capacity, for the methylene blue removal in wastewater. Yeah, we have agricultural or industrial material absorbent. Yeah, we can use the peels, bugs, the leaf, the fly ash, as well as the fiber. For bioabsorbent, we can use algae, bacteria, other biomass, as well as the fungal. Yeah. For natural material, the clay minerals as well as zeolite, can also be classified as natural source for the development of the absorbent. So actually, I have been narrowing. Yeah, I've been narrowing the scope. Yeah, if we look back, into my third slide. Yeah, so these are the overall technology that can be used. Yeah, for the removal of methylene blue. Yeah, MB is the methylene blue in wastewater. Yeah, so that's I have narrowing the I have narrowing the scope, so that you can see the topic today is on absorption technology. Yeah, but if we are going to use the carbon-based absorption, there are many types of the absorbent, 1, 2, 3, 4, 5, 6. Yeah, but the one we are going to discuss in detail, in our syllabus is only this one. Why this one? Why only modified activated carbon and activated carbon? Because they are mainly used for the treatment of water and wastewater. Okay, next. Yeah, so these are the sources, of the materials. If you are talking about agricultural waste, agricultural sources, then peels, bugs, leaf fiber, and fly ash, can be used to develop the absorbent. If bio absorbent, algae, bacteria, and fungal. If natural material, clay and zeolite can be used to develop the absorbent. Okay, my next slide is on the mechanism, of the absorption process. Okay, the mechanism of the absorption process is involve few interaction. Yeah, if you notice, this interaction also exists, in during coagulation process, which is electrostatic interaction as well as van der Waals forces. So they are not exactly the same mechanism, but part of the mechanism that involve, during coagulation process does also involve during absorption process. However, there are other process, that involve, there are few more mechanism that involve, including surface complexion as well as ion exchange, hydrogen bonding, the surface diffusion, as well as intraparticle diffusion pores. Yeah, so these are the difference, between the coagulant as well as the adsorbent. Yeah, in coagulant, during coagulation process, is only involve the electrostatic interaction as well as van der Waals forces. Yeah, the attraction process as well as the repulsive forces. While this one, there are many others mechanism that involve, because it's require the material to is not only ion attraction. It's not only the method of repulsive and attractive forces, but it's involve other complex mechanism, because we want the purpose of the absorption technology is to allow the particles, the one in red here is the pollutant, to stick on the surface. Yeah, this is considered as the surface. Why? Okay, if you look at on my left side, we have if you look at on my right side first, this is the system of the absorption without any impregnation process. So after we have exposed the material into the acid, so that it will develop the pores. If you expose the orange peel, the charcoal into the high temperature, into acid, high temperature condition, in acid, then it will start to develop the pores. So having the pores will allow more pollutant to stick within the pores of the adsorbent. Okay, I repeat. So this is very important point that you have to understand. On my right side, is the adsorbent without any impregnation process. Impregnation process is the process where we promote the development of pores on the surface of the adsorbent. After exposure to high temperature as well as into acid, the pores will start to develop on the surface of the adsorbent. So adsorbent just now, it can be derived from the agricultural waste like the biomass, peels, the bugs, the charcoal. So it can be derived from any types of biomass. So once you expose to high temperature as well as to the acid, the pores will start to develop. The higher the temperature, the more pores will be developed. So having more pores will allow the more pollutant to stick on the surface of the pollutant of the adsorbent. Okay, so these are the concept of having of using the adsorption. Okay, I currently have two PhD students who are currently working on this topic. One on the removal of methylene blue, another one he is working on the improvement for the water treatment process, for the removal of a volatile organic compound. Okay, figure 5 is the adsorption procedures using various carbon-based material. Okay, these are the real photo of carbon-based material. This is the photo of graphene, carbon aerogel, activated carbon, carbon nanofiber, biochar. Next one is the schematic clarification of activated carbon derived from bio waste and its potential use. So we can use straw. We can use unwanted vegetables. So that the chemical activation or the physical activation, the impregnation process just now, whether we use acid, you use any types of chemicals, or you use steam, air, or carbon dioxide, they are classified as physical activation, will develop a very good and excellent activated carbon, where it can absorb the pollutant. Okay, so before we go further, I think we can watch this short video. I can. Okay. You can spend some time to watch the video.
Absorption and adsorption. Some tea accidentally falls while you're studying. What is the best way to remove it off immediately? Click on the right option. Yes. Now watch the tissue paper suck away the spilled liquid quickly. If we had used ordinary paper, the tea would not be completely absorbed. Tissue paper absorbs a liquid, and ordinary paper adsorbs a liquid. How are these two different? Let us learn more on them. Let's understand absorption and adsorption a little better. Absorption is the passage of one substance into or through the bulk of another medium. The absorbed substance spreads to saturate the whole of the medium to form a solution. The mixing with the other medium's environment is so well that one fails to recognize its existence as a separate entity. In contrast, what happens during adsorption? Adsorption is the addition or sticking together of molecules of a gas, liquid, or dissolved solids to the surface of a solid or sometimes a liquid. The molecules are loosely held by the surface and can easily drop off. Let's see the difference between these processes. Absorption is seen in common day examples. Perfume spray is absorbed by our skin. Crisp finger chips turn soggy because they have absorbed moisture from the air. One substance is well soaked into a different medium. What about adsorption? Here is a jar containing a red dye dissolved in water. Look, what happens when a solid pellet of carbon is dropped into the jar? Well, isn't that surprising? The red color has almost disappeared in the jar. Why? The charcoal pellet has minute pores on its surface that cause the colored particles stick to it. The red dye undergoes the process of adsorption. Shake or warm this jar, and lo, you get back the red color. Adsorption can be easily reversed by simple heating and is transitory. When a substance is absorbed in a different medium, it's called absorption. Usually, absorption cannot be reversed by simple means, although it may also be temporary. Now let's focus on adsorption by carbon and some practical applications. We could use adsorption for such diverse things like in deodorizing air in a refrigerator, decolorizing sugar solution, and controlling excessive acidity. Activated charcoal in a gas mask attracts toxic gas molecules, allowing the person wearing the mask to breathe fresh air. Drag the carbon pellet to each of the units displayed here, one by one, and observe the reactions that take place. Identify whether a solid or liquid or gas is adsorbed by carbon in all these cases.
Forget about attending trading webinars because I'm going to train you for free. That's right. Keep watching and I'll tell you how it works. Hi, Thomas in here. You maybe have attended at least one webinar in the past year. I know those webinars, those that give a brief overview, then ask you pay thousands of dollars to learn the rest. So I wanted to do something different to help more traders.
Yeah, so these are the the simple story, how can we differentiate between adsorbent as well as
Studying
adsorbent?
adsorption, huh? Got a big test coming up? Staying up all night studying? Let's see how we can make sure you get some shut-eye. At first, adsorption looks like it's just stuff sticking to other stuff. But if you take a closer look, you'll see that there's more to adsorption than that. Adsorption is the adhesion of particles on free surfaces. Adsorption happens when atoms, ions, or molecules attach to the surface. Adsorption happens when atoms, ions, or molecules attach to the surface of a substance without entering it. They
So the
hang
point is actually stick on the surface without entering it. Yeah, without entering it.
out on the surface. An example would be chemicals in a liquid sticking to a solid surface. If we zoom in closely, closer, almost there. You've probably seen an image like this in your textbook before. Ions, which are chemicals with a charge that are attracted to soil particles. It's a bit more complicated than just stuff sticking onto other stuff. The outer sphere and inner sphere complexes are attaching in different ways. It looks like some of them can easily be knocked off or exchanged with other compounds in the solution, while others are holding on tightly. You can clearly see at this view how the hydration sphere surrounds the outer sphere complexes and not the inner sphere ones. Can you see what the difference is? Water. We call it hydration. Water is dipolar, which means a water molecule has a positive side and a negative side. An ion bound by outer sphere adsorption is surrounded by a hydration sphere, a collection of water molecules that are physically attracted to the ion because of its charge. Hydration spheres can form around both positive and negative ions because water has a positive and negative end. We see water molecules gathering around a cation and an anion, clearly showing the different ways they attach based on polarity. Opposites attract, just like with magnets. Since water has a positive and a negative side, it can align with either type of charged ions. This same physical force attracts the water molecules, with the ion in tow, towards the charged solid surface in soils. The water is acting as a buffer between the ion and the solid mineral surface. The ion sticks to the surface, but only loosely, so it's easy to remove again. This is what happens during ion exchange. It's like a chocolate-covered pretzel. The chocolate is stuck to the pretzel, but you can easily chip it off, although that seems like a lot of work to eat the plain pretzel. We say hydration sphere, but the ion doesn't need to be completely surrounded. Even just one water molecule between the ion and the surface is considered outer sphere adsorption. Outer sphere adsorbed ions are easy to remove. They can be knocked loose by physical force, readsorbed back into solution, absorbed by plants, or even leached away and replaced by other ions with a similar charge. Since this adsorption process is entirely physical, it is called fissorption. Without water, though, something different happens. The ion shares some electrons with the surface. This is called a covalent bond, ligand exchange, or anion penetration. This means that a brand new substance forms at the boundary of the surface. The formation of a strong covalent bond during adsorption creates a new chemical compound. So this process is called chemisorption. Monodentate inner sphere complexes attach at 1 point. Bidentate complexes attach at 2 points. Polydentate complexes attach at 3 or more points. In adsorption, the more dentate links, the stronger the bond, and the harder it is to free the adsorbed ion. And in chemisorption, you don't even need a charged surface. It's like baking a cake. You start out with flour, eggs, milk, and sugar, but once you bake it, you can't separate the ingredients. So to review, fissorption is like the chocolate-covered pretzel. Chemisorption, which is fusion, is like the chocolate cake. Anyway, this new substance locks the ion away, so it can't be knocked away from the surface, or taken up by plants or bacteria. The rate at which these happen is different too, which is why we have to run so many adsorption experiments. Outer sphere adsorption is a physical process. It's fast, and all it needs to occur are dipolar molecules like water and a charged surface. Inner sphere adsorption is a chemical bond, so it only happens in more specific circumstances. You've got this. With the naked eye, adsorption may look like just one process, but when we get down to the molecular level, we can see it's actually very complex. These two processes have a lot of implications. Whether fertilizer and nutrients can be used by plants, what percentage of impurities can be caught by a water filter, and much more. It's all part of the wonderful world of adsorption. Oh, sorry. Now you can get some well-deserved sleep.
Okay, so this is part of a good video, which I believe that is very useful for us to understand better about the mechanism. The first video on the difference between the absorption and adsorption, and the second video on the mechanism that involved during adsorption process. Okay, so this final video is how to make an activated carbon, yeah, from charcoal. Yeah? Because charcoal is the most common activated carbon that being used in water treatment plant. Okay, so this is how real activated carbon looks like in a water treatment plant. Hopefully that during our visit we can have a look at in one of the filtration tank, because normally in a water treatment plant we should have at least two tank, yeah? So that one will be working and one will be in a standby mode, yeah? So that hope that we can have a look on the real activated carbon which is available in a filtration tank. Okay, so let's continue our lecture today. Yeah, on this is the definition which I have defined earlier. That is the surface activation. Yeah, or surface phenomenon with a common mechanism for the removal of the pollutant. Yeah, it's a chemical as well as a physical process. Yeah, and it's involved the van der Waals forces, yeah, for the physical sorption, for the chemisorption covalent bond, and it can also happen because of electrostatic attraction. So which has been explained earlier in the video. These are the forces involved during adsorption process. So overall is surface sticking the pollutant which stick on the surface of the media. Yeah. So in a water treatment plant or wastewater treatment plant is a liquid or gas, which is attracted by chemical or physical bonds to the solid surface. Yeah. So the purpose of the activation process is to allow more pores to develop, to activate the pores, because the more that the pores they are available on the surface of the adsorbent, so that the more pollutant can be absorbed, so that large networks can be developed. So normally when we develop the adsorbent, we will introduce high temperature, or we will expose the adsorbent to chemicals or acid, so that will improve the pores that which is available on the surface of the adsorbent. Apart from the development process, before I go further on the factors, maybe we can spend some time to look on the because I have few final year project student, which has completed earlier on the topic on the adsorption. So maybe we can, oh, hey. Okay, maybe we can have a look. With 9. Oh yes, this one. Yeah, this is the FYP poster prepared by my former bachelor student. Yeah, she has graduated 32 years ago. So she actually has developed the adsorbent, which is derived from sagu pambak. Yeah, this one is not very common in peninsula of Malaysia, but very common. Anyone from Sarawak, you must be familiar with the sagu pambak as well as the sawdust. So the purpose of the development of this adsorbent is for the removal of ferrum in groundwater. Okay, she collected groundwater from Negeri Sembilan. Unfortunately, the ferrum concentration is too high in that sample. Yeah, so you can see this is the color of the groundwater before it being exposed to the adsorbent. Yeah, and this is the next photo is the color of the groundwater after treatment using sagu pambak. And the next one also after treatment using the sawdust. Yeah, she used 2 types of adsorbent for the removal of ferrum purposely. Yeah, for the removal of ferrum. But you can see here, even though on the adsorbent were developed for the removal of ferrum, it has also effectively removed the COD, the total solid, as well as the color. Yeah, so. Uh, so the process involved is wash the adsorbent with distilled water, and she has oven dried for 105 degrees Celsius for 24 hours. Yeah. So after that, she has exposed using the chemical treatment, the adsorbent, and for 80 degrees Celsius for 2 hours and leave overnight at 50 degrees Celsius. And she has weighed the adsorbent at different weight. Okay, this I will explain to you later. The needs to find the optimum dosage is very important when we employ an adsorbent. Otherwise, it will react like during coagulation process. If you remember, we have to conduct a coagulation study, so that we can find the best dosage to be used. So that this is the best dosage to be used, so that we know the best dosage to be used for the removal of certain pollutant. So in this case, she has developed 20 gram, 50 gram, 100 gram, and 150 gram of the adsorbent, so that she will expose all this adsorbent at the same volume of water. Yeah, the same volume of water. So that after certain period, then she monitor the removal rate. So these are the sawdust, yeah, and sagu pambak. That was the time when she used resin. Yeah, she used resin to allow them to stick to each other. So the groundwater volume is about 500 ml. These are the different dosage of the sawdust. These are the different dosage of the sagu pambak. Yeah, so the purpose of having a different, various dosage are to find the best dosage, the optimum dosage. Yeah. So let's say 50% is sufficient, 50 gram is sufficient to remove up to the standard requirement, so that we don't have to use 100 gram of the sawdust. Yeah, we try to minimize the weight of the dosage. Yeah, we try to minimize the dosage of the adsorbent. Yeah, but at least we can achieve the target removal. Yeah, that is the purpose of doing the treatment. On top of that, whenever you study an adsorption process, that you cannot avoid to study and to analyze which one is the isotope, the isotope which is suitable for these types of adsorbent. So now there are two popular isotope, which is a Freundlich isotope as well as the Langmuir isotope. Yeah, so the difference between Langmuir and Freilich isotope are first their names. Yeah, second, we would like to know whether the adsorbent that we have developed, yeah, is the behavior of the adsorbent prone to absorb water or prone to absorb the pollutant. Okay, but never mind. This one we shall conduct the calculation later. But for now, I would like to explain to I would like you to see the real data. Okay, these are the absorption, and she has conduct the filtration as well as the aeration. But before she conduct the aeration as well as filtration, you can see the color. This is the concentration of color in her raw groundwater sample. After adsorption using sagu pambak, the color has reduced to 7 for sagu and the sawdust to 11. For the COD, you can see that the real concentration is 85%, 85 milligram per liter. It's been reduced to 5 and to 2. Total solid, from 1000 reduced to 800 as well as 891. Total solid is not very much, it's not very good, in terms of removal rate when we employ adsorbent, because adsorbent are prone to remove the dissolved solid. So to remove the total solid, normally we have to use the coagulant, not an adsorbent. Total dissolved solid, you can see the reduction. The ferrum concentration, for the target for the development of the adsorbent is to remove the ferrum. So in this case, she managed to remove the ferrum from 0.83 to 0.11. Actually, even though you can see the concentration is not too high, 0.83 je pun, but the problem is exceed the allowable limit, and also the color. This, when you see the color of the raw water is murky like this, so that indicates the reaction of ferrum and oxygen, that which is known as ferrous oxide. So that is why the needs for the removal of ferrum. Okay, all right. So let's continue. So factors affecting the adsorbent. Okay, there are few factors normally govern the adsorbent, like coagulation process. So the first factors are the pH. pH really govern the sorption capacity. The sorption capacity are really governed by the pH, because most of the adsorbent which has been developed are very good at lower pH. So these are the obstacles. When we develop the adsorbent, unfortunately, we cannot commercialize the adsorbent which we had developed due to the impracticability. Why? We have to reduce the pH of the wastewater to 2, then only the adsorbent will function well, and that is not very practical. So this is the obstacle, I must say, when we develop the adsorbent and we try to commercialize them, because pH is one of the factors that really govern the sorption capacity. The next one is the dosage of the adsorbent. So the dosage of the adsorbent is the one that I did share with you just now. These are the dosage. The dosage of the adsorbent. So first, when we after we have developed the adsorbent, then we have to study what is the best dosage to be used to avoid any wastage. First, to avoid any wastage, and second, to ensure we have an effective removal. Because too little also will not allow for an effective removal. That's why we have to study the dosage of the adsorbent. We have to investigate the best dosage to be used. The next one is the effect of contact time. Effect of contact time is another parameters that we have to consider, because the longer that we allow the contact between the adsorbent as well as the water or wastewater to be treated, definitely it will improve the efficiency. But how long? Because we have to consider on the operational time. So this is why that contact time one of the most important parameters to be monitored. Yeah? So the best adsorbent should be able to remove the pollutant very quickly. So if I can go back to this slide, and you can see there are carbon nanotube here. Carbon nanotube is one of the most advanced version for the adsorbent technology, because it can remove, they use the technology of nanoparticles for the removal of pollutant. So definitely they can remove the pollutant very fast. However, they are not very preferable for water treatment or wastewater treatment due to cost, and they are not very much practical as compared to the activated carbon. Alright. Next is the effect of temperature. First, the temperature of liquid. Second, the temperature that we use to develop the adsorbent. So as I mentioned just now, my previous student, she used temperature of 105 degrees Celsius during the development of the adsorbent. Once, meaning to say that once she has collected the sagu pambak as well as the soda, she will expose them to the high temperature. So that were many years ago, I have one student who studied the absorption capacity, the capability of the adsorbent to absorb the pollutant at different temperature. So first he prepared the adsorbent and exposed at 100 degrees Celsius. Another one, the same adsorbent, but he exposed at 200, and so on. So that we can see that the higher the temperature that you use during the development of the adsorbent, the better will be the absorption capacity, and the better will be the removal rate of the pollutant. Why? Because the higher the temperature, we can it will promote more pores, pores, pores to develop within the surface of the adsorbent. Okay. Okay. Next. Okay, the effect of time. So this is the example of removal of ferrum. So you can see the percentage of the removal after 20 minutes. So this is the graph from the student which I shared with you the poster just now. She studied on the removal of ferrum using sagu pambak. Okay, this one is the top graph is using the sawdust. Another one is using the pambak, the sagu pambak. You can see after 20 minutes, the removal rate started to flatten. The graph started to flatten because it has achieved the what do we call as equilibrium concentration. Equilibrium concentration. Equilibrium concentration is the condition where that is the maximum removal capacity of the adsorption. For example, when you start the experiment, the initial concentration of the ferrum in the wastewater is 10 milligram per liter. 10 milligram per liter is the initial concentration of ferrum in wastewater. And you put the adsorbent. After 5 minutes, you take the reading. You will see that the concentration, and you take the sample, for the ferrum measurement, and you notice that the ferrum concentration has reduced to 8 milligram per liter. So after 10 minutes, you check again. It has reduced to 7 milligram per liter. After 15 minutes, you check again. It has reduced to 6 milligram per liter. After 20 minutes, you check again. It has reduced to 5.8 milligram per liter. After 25 minutes, you check again. It's still at 5.8 milligram per liter. After 25 minutes, you check again, it's still at 5.8 milligram per liter. So that is what I mean by concentration at equilibrium. Meaning to say that for how long that you will leave the adsorbent in wastewater, it won't absorb anymore the pollutant. So it will start to flatten the graph. Depend on the capacity of the adsorbent, how long it will take. sometimes it will take, if you use nanoparticles, you will be having the flattened graph less than 5 minutes if you use nanoparticles. Yeah? But if you use common activated carbon, it can take up to 20 minutes to 3 hours. Okay. All right, so how to identify the optimum dosage? Yeah, this are the another example from my previous student. He used orange peel and banana peels. Yeah, so the raw sample is 7 ml. As I said just now, whenever you would like to study the optimum dosage, you have to use the same volume of water to be treated. Yeah, or raw water or raw wastewater. Then you can you can use various dosage of the adsorbent. In this case, he used 5 to 30 gram. Yeah, so you can see these are the results. Yeah, so at 5 gram per liter, at 5 gram of the adsorbent, the manganese which has been removed about 59.8%. Yeah, at 10 gram 73. At 15 gram, the manganese has been removed about 84%, the removal rate. At 20 gram, 91%. At 25 gram, 94.5. At 30 gram, 94.5. So this indicates that the more the adsorbent that you put in water or wastewater to be treated, the higher will be the removal rate. But nevertheless, after certain period, even though you keep dosing the adsorbent, there will be no more difference. Yeah, for example, like 25 and 30. Yeah, there will be very little difference in terms of the removal rate. Yeah, so if you are the water treatment operator, you are to select 25 gram. You are to select the lower adsorbent dosage because we would like to save some capital cost, yeah, as well as operational cost. Yeah, so if we are to compare between the orange peel and banana peel, you can see at 5 gram at 5 gram dosage of the banana peel, it remove about 60%. 10 gram 75, 15 86, 20 82, yeah, 25 and 30. You can see the removal rate are more or less the same. But if we are to compare the effectiveness between these two adsorbent, we can conclude that the banana peels perform better, yeah, as compared to the orange peel. Why? Because at the same dosage, they have a better removal rate. Okay, you have any question regarding on optimum dosage as well as effect of time? Yeah, okay, saya laju sangat, yeah, because this is very common. Only this semester I don't have a student running on this topic. In the previous semester we do have. Maybe in the following semester I will offer another topic for the final year project on adsorption technology. So so in conclusion, you have to understand this because in our calculation later we are going to use all of this value. Yeah, that's why the concept you have to get the concept. Yeah, so I repeat. Yeah, so you can see that after 20 minutes the graph is almost flattened. Why the graph is almost flattened? Because the removal rate are more or less the same. Why the removal rate are more or less the same after certain period? And how do we relate between this graph, this slide, and the following slide? Yeah, you see the variables are not the same. These are being conducted. Yeah, this graph represent one of these. I'm not sure which one, but I believe that at dosage 30 or dosage 25. Yeah, because is achieved almost 200% removal. Yeah, so every dosage that we have selected, we have to develop the same graph. Yeah, where we are going to monitor how long it will take to remove the pollutant, what is the equilibrium concentration, what will be the highest removal rate that can be achieved at each of the for each of the dosage that we have applied. Yeah, so these are the flow chart to show the preparation of the orange peel and banana peel. So collect of natural, this one is only orange peel. First, she collect the natural orange peel, wash with distilled water, and dry in the oven at 65 degrees Celsius, and ground and sieve to size less than 250 micrometer, and re-dry in the oven at 65 degrees Celsius for 24 hours. Yeah, and she exposed to acid sulfuric acid. Yeah, and this is how she conduct the absorption study, yeah, to see the effect of time, yeah, to see the effect of time, because normally when we would like to see the effect of time, it's better for us to run with the sterile, yeah, so that the adsorbent will be well mixed with the water or wastewater to be treated. Yeah. Okay, next one is on absorption isotope. As I mentioned just now, whenever we conduct absorption study, we cannot avoid. We have to study on the Langmuir isotope as well as Freundlich isotope. These are the most popular isotope that being used, yeah, to represent at constant temperature of the amount of solid adsorbed per unit of adsorbate weight. Basically, the same process that we are going to, the same parameters that we have to figure out whenever we conduct the absorption study, but yeah, whether our adsorbent prone to Freundlich isotope or close to the Langmuir isotope, that will explain the behavior of the adsorbent that we have developed. Yeah. Okay, never mind. Okay, this is already explained. Yeah? So if we are talking about activated carbon, yeah, there are two types. Yeah? First is PAC, the next one is GAC. Yeah? PAC is powdered activated carbon, GAC is granular activated carbon. So PAC, the diameter less than 0.074, while the granular, you can see, yeah, the granular, the size is bigger than 0.1 mm. Okay. So activated carbon are very good for the removal of inorganic and organic as well as suspended solid, but they are best for the removal of organic matters including TOC, VOC, as well as other organic. Yeah. Okay. Adsorbent is involved carbonization of agricultural waste. Yeah. So when we are talking about adsorbent, in this country, we are focusing more on the agro waste derived adsorbent. Yeah. So carbonization is the process, yeah, is the development process where we expose whether to acid, we expose whether to a temperature, or we apply the steam, yeah, so that we can activate, yeah, the pores on the surface so that it will become an effective activated carbon. Yeah. So you can see, yeah, on my left side is the raw carbon material, uh, on my right side is the activated carbon material. Whenever we have exposed to acid or any kind of chemicals or high temperature, the pores will develop, yeah, not only to develop the pores, but it will also provide the linkages. Yeah? So the pores and the linkages are the important characteristic for a well-developed adsorbent, otherwise it will not absorb the pollutant. Okay. So these are the carbon granule at work. After water will pass through the adsorbent, it will produce the clean water. On top of that, we also have a typical downflow activated carbon contactant. Okay, activated carbon very fairly familiar in this country, because if you have a water dispenser, yeah, so normally they will acute with the activated carbon. Yeah, so activated carbon will not be able to remove all minerals. Yeah, to remove all minerals, we have to use reverse osmosis lah. Yeah, but still they can remove some of the importance mineral. If you would like to reduce the concentration of the mineral, they can. But activated carbon basically cannot remove all mineral. All minerals can be eliminated using a membrane technology, in particular reverse osmosis. Yeah, so the activated carbon that we have developed area are now being loaded into the downflow activated carbon contactor. Yeah, so it can be used to produce the clean water. On top of that, GSC contactor are not only being used for the treatment of water or wastewater, they are also familiar for the treatment of gases, of the polluted gases, as well as for the treatment of ammonia as well as hydrogen sulfide, odor treatment, odor treatment in wastewater treatment plant. Yeah, so this technology is not new, but they are considered as the post-treatment or polishing stage because in wastewater treatment, because they are not being used as the major treatment, they can only be used as the secondary treatment or extra treatment to remove the substances left in treated wastewater. Okay, so normally column is very common, commonly being used, so that we can pass in and pass out the water, for the removal. Any question? Okay. Next is on. Okay, we have downflow and outflow. So let's see one by one. Downflow columns require frequent backwashing. Advantage is absorption of contaminants can occur in a single step. So this is the downflow series. What is the difference between outflow and downflow? So if downflow, water will coming in from the top part of the column. This is the bioreactor lah. In here, you'll be loaded with the inside the bioreactor. You'll be loaded with the activated carbon. So whether it's downflow or outflow is depend on the configuration of the water flow. You can see that whenever we use outflow, water will come from the bottom part of the reactor. That is known as outflow system. Okay, so as carbon absorb the contaminants, density of carbon increase and encourage migration of heavier carbon downward. So let's say, in this case, if we pump in water into the column, so the density of the carbon increase, when it absorb the contaminant. So once it's absorbed the contaminants, the density will increase so that it will migrate to the bottom part of the system. So that will encourage the migration of heavy carbon downward. So that the lighter carbon will move to the top part of the column. Okay, these are the equation we are going to use later. Actually, we have to plot the graph, to identify whether the carbon that we have developed, are more suitable to the Freundlich isotope or Langmuir isotope. To use the equation, we have to use the value of 1 to n value. Depends on the pollutant that we would like to remove. They have different factor to be used. They have a different factor to be used. So apart from exploring the isotope which is more suitable, we also need to calculate the bed life. What is bed life? Bed life meaning to say that how long that we can leave the water and wastewater to be treated using certain types of activated carbon without we have to wash them. So bed life is the period before we can conduct the cleaning, whether the physical cleaning or the steam cleaning or the chemical cleaning. So that are the bed life before we have to replace with a new batch of activated carbon. Okay, so we are going to use this equation. I think we have 2 examples today. And overall, low-cost bio-waste derived adsorbent can be categorized and defined in terms of their initial cost. If you use agro waste, definitely your initial cost will be lower. Local availability. So what for if you would like to use sagu pampak, if it is not available in the marketplace of Malaysia, you better find something which is easily to be found. The stability, the eco-friendliness, the transportation, the applied treatment process, the recycling, the lifespan, the regeneration potential. Regeneration is a new term lah, in the topics of adsorption, because sometimes we can develop the adsorbent for a better removal, for the best removal of the pollutants. Unfortunately, when the time reaches where we have to remove the adsorbent, then we have no idea what to do, okay, with the use adsorbent. So this is where the regeneration potential comes, the desorption process. So the desorption process can be done using weather techniques, chemical techniques, where alkali, the bioadsorbent using the acid, and the biomass using complexing agent. So these are the agents that can be used to dissolve the pollutant which already stick on the surface of the adsorbent. So in other words, adsorbent stability and affordability are important characteristics that will influence the applicability of certain adsorbent. We have to ensure it's locally available, the easy to transport, the economic feasibility, and also regeneration is other important section to be looked whenever we produce the adsorbent, because we have to consider on the how to dispose the adsorbent. That's why we have to regenerate the adsorbent and it can be reused later. Okay, so I think that's all for our lecture today. But not yet finished. We are going to explore the example and the calculation. Okay. Okay, example 1, lecture 9. Table 1 shows set of data for an adsorption study of ferrum removal in groundwater treatment, which was conducted in 5 different containers. The volume of groundwater in each container is 1 liter. Given the initial concentration of ferrum in groundwater is 25 milligram per liter. Okay, first, plot the Freundlich and Langmuir adsorption using given data. So let's imagine that you have developed the adsorbent. So now you are going to classify the adsorbent into 25 gram until 250 gram per 250 gram. Then all of them are going to be exposed into 1 liter of the groundwater. So after the exposure to 1 liter of the groundwater, then you have to identify the concentration at equilibrium. So for example, at 25 gram, it achieves equilibrium at 10. So let's say you put 200, you achieve the equilibrium at 25. Whenever you use 25 gram per liter, you achieve the 25 the concentration at equilibrium at 10.2 milligram per liter. So the higher the dosage, the better will be the concentration at equilibrium. Okay, so for example, at 250, the concentration of equilibrium is 1.4. Okay, next you are going to plot the Freundlich and Langmuir adsorption using the given data. Okay, what we should do, you have 6 different containers, and you know that the initial concentration of the ferrum is equal to 25 milligram per liter. Okay, and the CE, CE is the concentration of the equilibrium. CE is stated in the question here. Okay, then column number 4 is X equal to C naught minus CE. So C naught is equal to 25 minus CE is equal to 10.2. as x is equal minus 10.2 equal to 14.8, and you solve for this column. Okay, next is the m is the is the weight. Yeah, just copy and paste here, and x over m. Yeah, x over m, m is available here. Yeah, m is available as 25 gram. Yeah, so what is x? Yeah, what is x? X is c naught minus ce. Yeah, and you can solve for column number 6 and 7. Yeah, 6 is x over m, while 7, yeah, 7 is equal to ce. Sorry, column number 7 is equal to ce in bracket x divided by m. Okay, so CE are the most important value to be used now. X here, yeah, or divided by M. Okay. When you can plot the graph of Freilich isotherm, yeah. Okay, to plot the graph of Freilich isotherm, what you should do first? Okay, to plot the graph of Freilich isotherm, okay, to plot the graph of Freilich isotherm, you need the value of x over m as well as CE. Okay, this value you have identified before. So x divided by m over CE. Yeah, the x-axis is equal to CE. Okay, so bear in mind, do not log the value. Please log the graph once you have plotted. Yeah, sorry, you have to log the graph. Yeah, you have to log the axis. Yeah, you have to log the axis. In this case, I have logged the axis, the y-axis as well as the x-axis. Okay, let's see one by one how we can plot the graph. Okay. Okay, so if the x over m, x over m is column number 6, yeah, and the y-axis is the CE. CE of column number 6 versus column number 3. Yeah, so you plot the graph. Let's see, for example, point 0.592. This is from 10.2. Yeah, 10.2 is that here. So 0.428. Yeah, 0.428 is here. Yeah, versus the 3, if I'm not mistaken, 428 and 3.6. Okay, you plot one by one the graph and you check the R squared. Yeah, once you have plotted the XM versus CE, the graph plotted is more to linear, thus fit a Freilich isotherm. Yeah, so R squared is equal to 0.839, which is 83% of this value fit. Yeah, so when it tells you that the R squared, the correlation coefficient, is equal to 0.83, this indicates that 83% of this value fit the regression analysis. And 93% of this value fit the regression analysis in models and more positive relationship. Okay, so therefore Freilich isotherm present a better regression. Okay, let's look at the Langmuir isotherm. Okay, for Langmuir isotherm, we want to plot C over X over M divided by CE. Okay, C over, just now only X over M, but this time around CE divided by X over M. So whenever you plot the graph, you will see that the R square is not too good, yeah, in Langmuir isotope, yeah, because is R square is equal to 0.27, yeah, 0.27 is considered is considered as a weak correlation. Okay, so this one to CE X over M, yeah, versus CE value. Okay, the plot of the Langmuir isotope is curvilinear. Then you can see the plot of the isotope is curvilinear, so that the use of this isotope is appropriate. Okay, so if you got a curvilinear, then the isotope is not appropriate to you. Okay, so the value more to zero means the relationship between these variable. Okay. Mm, determine how much granular activated carbon will be required to take an effluent flow of 6,500 meter cube per day to produce bromoform concentration of 0.09 to 0.05, 0.09 to 0.025. Given the Franck isotherm coefficient for bromo is K point bromoform KF. This one is from the table just now. Yeah, the table is which is available in my notes. This table. Okay, so and 1 over n, yeah, also available in the notes, equal to 0.52. Okay, let's see the calculation one by one, because in this calculation you are going to determine the bed life. Is a very good calculation. Okay, effluent flow rate is equal to 6,500. Initial concentration of cobalt, CO is cobalt, is equal to 0.09. Final concentration of cobalt equal to 0.025. Okay, so Franck capacity factor is 19.96. The Franck intensity factor is equal to 0.52. Okay, granular activated carbon density is equal to 34.4 kg per meter cube. Yeah, then empty bed contact time is equal to 10. And sometimes we can predict this, yeah, empty bed contact time, because these are the period, yeah, where we will have to expose the developed adsorbent. So empty bed contact time is extremely very important to identify. Okay, what you need to do first is to estimate the GAC usage rate. Okay. Okay, you can spend some time to have a look at this calculation. Yeah, okay. Can I? Let me adjust a little bit. Okay. Now I want you to explore the calculation up to carbon required 1552.78 kg. Okay, explore the calculation first. Yeah.
Doktor, saya rasa doktor terlupa nak buka mic.
Okay, so how long that I have switch off my microphone?
From warna hijau punya pen marker.
Sorry?
From green marker.
Oh, green marker. Alright. Okay, thank you, Muhammad. Okay. Alright. Okay, the effluent flow rate. First, you are given the value in meter cube per day, then you convert into liter per minute. Okay, that is very basic. Yeah. Then you are given the 10 minutes empty bed contact time. Yeah. So how to determine the empty bed contact time? Empty bed contact time, you can determine there are two methods. The first one is by volume of the GAC in the column divided by volumetric flow rate. You will get the time. Yeah. The flow rate, volume of the granular activated carbon that you would like to load in the column divided by the volumetric flow rate, or the length of the granular activated carbon in the column, the length, the length of the packed granular activated carbon. Let's say we have this, these are the activated carbon, these are the activated carbon. So it can be the length of this, L, divided by the velocity of the water. The velocity of the water, the V of the water in. The water or wastewater that we would like to treat lah. Okay, so first volume, whether the first method, you can determine the empty bed contact time by volume of the GAC. How much the is GAC that you want to load in the system divided by the flow rate. The second method is the length. The length here divided by the velocity of the water. Okay, therefore, you solve for this equation. Therefore, the mass of the granular activated carbon required for 10 minutes empty bed contact time is 1500.78 kg. Then determines the volume of water which can be treated using 10 minutes empty bed contact time. If we hope that, when we say that 10 minutes empty bed contact times, that indicates that how long that will take water to travel within the activated carbon which is available in the column just now. So it's basically how long that water will pass through from this point. Once it's entered the column, it will take to pass through from this point to this point. So that is what we call as empty bed contact time, EBCT. Mass of the then you determine the volume of water which can be treated at contact at EBCT of 10 minutes. Then mass of the granular activated carbon divided by granular activated carbon usage rate. Granular activated carbon usage rate. First, the mass you already calculated. The GAC usage rate 0.023, also calculated earlier. So that you will get the volume of water to be treated is 6.75 times 10 to the power of 7 liters. Then you determine the bed life. Okay, what is bed life? Bed life is the period where we have the idea how long that we can leave the activated carbon without cleaning. So in this case, we use a very simple formula to calculate the bed life, but we end up getting the result of 11 days. 11 days indicates that this is the suggested period where we have to conduct the cleaning. So what do we call as bed life? Normally, cleaning can be done 3 to 4 times. After the fourth cycle, then we have to change to the new activated carbon. But cleaning can be done. Cleaning is also known as desorption, because we would like to remove the sticky pollutant on the surface media, on the surface of the adsorbent. Okay, so these are actually the main target. And we would like to know how long that we can use the adsorbent. Sometimes when the student asks me they would like to design for a filtration system, I will ask them to determine the bed life for the material. Because then only you know that you have the idea how long, what will be the period that you have to change or you have to clean the filter media. Okay, so I think that's all the calculation. Yeah, I think that's all for today. Do you have any question? I think it's fairly long, the lecture today. First, in summary, there are two main examples, even though I put as example one, but there are two main calculation. First, you have to complete the table, then you can plot the graph. Plot the graph, Freundlich and Langmuir isotherm. So okay, you have to, when you plot both graph Freundlich as well as Langmuir isotherm, you have to know whether the adsorbent that you have developed is prone to Freundlich isotherm or Langmuir isotherm. Okay, Freundlich isotherm here indicates 83% of the regression rate, the coefficient correlation. Coefficient correlation between what? Between X over M as well as the concentration and equivalent. So that Freundlich isotherm fit the regression analysis model and more to positive relationship. As compared to Langmuir isotherm, you can see that when the graph give you a curvilinear graph like this, this indicates that the use of the Langmuir isotherm for these types of adsorbent is inappropriate, tidak sesuai. Inappropriate. So that these are the conclusion that required. Whenever you answer a question in final exam or test letter, you have to come up with this conclusion, because I will provide some marks. This indicates your understanding. It's very important to include the conclusion. Okay, and the second part is on the calculation. Basically, this is how to design a column filtration system. Is the activated carbon is a activated carbon that is loaded into a column filtration system. So you just imagine the water dispenser in our house that is loaded with the activated carbon, water in, so that it will be able to, when it can be both ways, whether it's upflow or downflow, as long as it will pass through the layer of the activated carbon. And this mainly to know the bed life, how long that we have to replace with the new activated carbon, or at least to clean the activated carbon for 3 to 4 to 2 to 3 cycle, and after 4 cycle we have to replace the activated carbon. So the limitation, overall, my observation as a researcher in this area, I believe that the obstacle whenever we apply this technique is the how to dispose the activated carbon, the used activated carbon. And currently we send to the landfill, but the activated carbon actually can be converted into a fertilizer. So but this still at research level, not yet implemented in the real situation. So the major obstacle is this one. We can use any types of the agro waste derived activated carbon for the removal of pollutant, for the physical chemical treatment. However, we are not yet into assessment from cradle to the grave. Assessment from cradle to the grave, meaning to say that we have no idea what are we going to do with the used activated carbon. We know that we know that it can effectively remove the pollutant, but after we have replaced with the new one, what I'm going to do with the use activated carbon? That is the obstacle and the limitation. Yeah? So I think that's all for today. You have any question? Yeah. Do you have any question? Okay, if there is no further question, next week is a week 10. Yeah. So maybe I will pass to you the assignment 3, and also don't forget, yeah, you have the project 1 that you have to complete, the only project that you have to complete. And my plan is to have your site visit will be in a week 12, which is on 14th of June. So and following that will be your test. Your test may be in week 14 or week 13. Let's see. Okay. So I think that's all for today. So thank you very much, everyone. Thank you for your kind attention. Any question?
No, doctor.
Okay. All right. Thank you very much, everyone. Sorry for the interruption. Bye. Have a pleasant afternoon.
Thank you, doctor.
Thank you, doctor.
Thank you.
Okay.
Sama-sama, sir.